Bam. All right. Testing 1 2 1 2 3. Okay, I think we are live. How is everybody doing tonight? I claim the live event will begin in a few moments. It should have already started, you fool. Why do you torment me? Should be going. Should be in a second here. Maybe. You two, why are you doing this to me? You're supposed to be live. You were the chosen one. That's all right. Okay. How is everyone? Tonight we're looking at Theano, and we're going to be using it to peek inside a convolutional neural network. Last week I sort of spent a lot of time going over what the hell a convolutional neural net was. This week I'm just going to hope to show some cool things. That's going to be the goal anyway. And I cheated a little bit. This time I actually did some work ahead of time. And I'm training a model right now. I'm actually going to interrupt it though. But what I really want to do, so I've got this pre-done stuff that I can fall back on that I've heavily borrowed. We're going to be trying to recreate that. If you want to follow along at home, I am looking at github.com/newmu/Theano-tutorials, and we're just doing the convolutional net tutorial. Can I increase the font size? I'm already on huge, man. I'm really sorry. That's something I'll look into. Yeah, I'm already on huge, which I understand you can't even see in here. That's something I'll look into doing in the future. Oh, really, I should just get a bigger monitor. Anyway, we're going to be following that that sort of tutorial. I've taken it and adapted it to my own. We'll see what happens. I've already trained a model, and I've actually saved off an old model, but I wanted to get a new one going. As always, we're going to be fiddling around with the MNIST digit classification dataset. And just before we actually start like building up the model here, I want to just show you a couple of things that I did. So previously I've trained the model, and let's say you want to look at some of those weights on, I don't know, the first layer. Remember, in a convolutional neural net, you've got these little boxes that are 3x3 or 4x4 or whatever that you're sliding around your image, and you're extracting a certain number of features, here 32. And so here you can actually see what each pixel value in that 4x4 box is. I think in this set I have darker is more. I might have it reversed. That's not really important. So you can see that at the top layer, you're looking at the image. Oh, these different features are pulling out different things. So that's kind of interesting. You can do this for any layer. You can look at what the weights are. On the first layer, like, it has a natural interpretation of, oh, that's what, you just take that pixel value. After that, it becomes not as obvious what you're doing, because then you're taking the previous layer's features and doing something with them. But you can see that you're pulling out other different things. So we'll be getting around to that. I always like to look at the final weights too. For me, yeah, check out what's going on here. For me, looking at the final weights is like saying, well, we built this cool neural net, and really we're just using that. We're just using the neural net to develop some new features, and then we're using those features to do a standard softmax or logistic regression problem. That's essentially what we're doing. And so to see those final weights, these are the 10 different digits, and you can see whatever, I think there happen to be 625 features, 625 neurons at this layer. And I've scaled it, it's all black and white here. But you can see, oh, well, all the features are slightly different things. Like here, you're not going to see any obvious patterns, probably. None of the neurons look dead. Maybe some of them do. It'd be interesting if you saw some patterns. So that's kind of cool. One more thing before we properly get going. We are going to have our neural net do a little dreaming. We're going to input some random information as our proposed image, walk it forward, and then we're going to ask, is that a 5 or a 0 or whatever? And then we'll walk that backward, and instead of climbing on the weights of the neural net, we'll climb on the inputs that are the image. So this is sort of what Google Deep Dream does. We're doing it on a much, much smaller scale here. But I was happy to get this, I think, working. Maybe not working. So we're going to be doing that in just a second here. Don't worry that I'm blitzing right through this. This is just to show what some of the cool things are. So this is sort of the essence of a 5. This is each iteration. Each time we start with this random image, we take it forward, and then we take it backward and we update it a little bit each time. Whatever reason I have this going top to bottom, then left to right. My sub figure needs a little bit of work. So there you go, and you get to the end. I just ran it for, I think, I must be 16 iterations. Yeah. Looks like that. I guess technically, well, yeah, whatever. 16 iterations, and this is sort of what if you input this image to the neural net, it says, yes, that is most definitely the most 5 thing I've ever seen. And, you can look at it and say, yeah, I guess that's sort of a 5. I would believe that. I might actually be wrong which number it is. But that's not what matters. And you could input a different random input and get out a slightly different random output image. That kind of thing. All right. But that's just the things I want to show you. This is what I've pre-built. But let's sort of walk through this, and let's walk through it by retyping it, which sounds a little crazy, but I find that'll keep me going at a slow enough pace that I'll have to explain everything line by line, and I won't be able to say, oh, don't worry about that, that's not important, but I'm probably going to say that anyway. Okay, first you have to import Theano. That's the deep neural network library that we're using. And then we got to import, for convenience, Theano.TensorST. I'm going to be switching back and forth from these things all the time. I bet I can still do this. I can. So it's going to end up being slightly different. We also are going to need to seed our random number generator. Oh, yeah. One second. Will I have a question section at the end? You can ask questions whenever. This is very free form. If you want to save it to the end, I'll try to save time. I often run out of time because I fail to succeed at all. Or send me an email or leave a comment. That way everyone can see it. Whatever you like to do, I'll roll with it. Right. This is our Theano.sandbox RNG MRG. What is MRG? That's a good question. I don't know what that is. Let's find out. Theano.sandbox.RNG MRG. What is this? Implementation of this random number generator. It's probably some kind of 31-bit random number generator. Let's take a look. Generator code and SSJ package by these guys. Let's just do a quick check on what it is. Java libraries for stochastic simulation. That's kind of cool. I guess it's part of Theano. I'm going to spend maybe 3 seconds looking at this. Random stream base, implemented in 32-bit integer arithmetic. Coefficients of the form, whatever. Has a period length of approximately 2 to the 185. That's kind of a big number. Okay. Well, that's cool. Anyway, that's how we're generating our pseudo-random numbers. I don't want to get in... that's something I don't want to get into too much. And you could use whatever you want for that. We're going to need Numpy. Numpy, of course, is the Python numerical library. It's actually built on 4chan and a lot of other stuff. It's super good. This next line, this is to load the MNIST data, since I have stolen it from this web page, github.com/newmu/Theano tutorials. Super good place just to get a simple bare bones. This is how you build this kind of machine learning algorithm in Theano. And I think there's a similar one for TensorFlow. Anyway, this just loads the data. Let me just show it to you real quick. Essentially, it just reads the data from a particular data set from a file because it's in, you download it with this bash script. I just edited it because it tried to save it to like /media/ something, and I didn't want to do that. So you can do that. That's this line right here. Anyway, we don't need that. I only had to change this a little bit. All it does is read in sort of a raw binary file into a Numpy array. That's all we're really doing for our training, for our testing data sets. So they just make that convenient. What do we got next? We need conv2d. So from, see if I can do this, Theano.tensor, and we could have said t.nnet.conv2d. Is that right? .conv. Import conv2d. This is what actually does the convolution operator. It's going to make it very convenient for us. It's sort of built in. You pass it the necessary parameters, like what's the stride, how big a box are we dragging along, is it 3x3 or is it 4x4, whatever. All right, that's that. What do we need next? Downsample. I'm just going to copy this one. This is how we're going to do the max pooling. So after the convolution, after we drag that box around, we'll look at every group of like 4 adjacent boxes, or every 2x2 block, and we'll say, all right, for a given feature, which one of these blocks is most activated? And maxpool says, just take the biggest one and throw away the rest. I don't care. So we're looking for the block that's most like a dog or whatever, or in our case, most like a 5. And this is called downsampling because you're reducing the number of samples. You've got this 2x2 block, and you want to only have one thing there. If you had, say, a 2x2 block and you wanted to have a 4x4 block, you'd be upsampling, and you would interpolate between your values. But that's not what we're doing. And so that's also why this is under signal. Signals processing does that kind of stuff a lot. All right, what else we got? Oh no, you gotta make sure I don't introduce horrible typos. Matplotlib. This is how we're going to be looking at pretty pictures. There are lots of plotting libraries out there. Matplotlib has been around a long time, and it's the one that I have the most experience with, so that's what I like to use. You can use whatever you like. I've actually been learning more of it recently to get these like subfigures and things working. All right, then %matplotlib. This is just for IPython. This will turn on sort of like the interactive mode, and it'll make it a little easier to deal with. Of course, I'm paranoid, and I turn on the interactive mode anyway. Hang on. Plot.style.use ggplot. This makes all your plots look so pretty. Oh my gosh. You should use ggplot over the default matplotlib every time. Almost guaranteed. It looks so, so good. Oh man. And this just turns on interactive plotting, so I don't have to say plot.show every time. So that's kind of nice. And I'm going to do Autoindent. This tells IPython, don't try to be smart about indenting lines I send you. And that's because I use this Slimux plugin to Tmux, so I can grab arbitrary lines and send them over. Note that my cursor never left my Vim session over here. So I'm going to have things already tabbed, and Vim's going to do that for me. So I don't want IPython tabbing as well, because it'll get real confused. That's something I've learned to do. Sys and pickle. This is just for saving the model, and I guess if I wanted to load the model, I would do that too. Pickle is the Python library for taking some kind of Python object and writing it to a file, and then later you can open up a new Python session on a whole totally different machine. As long as you have that file, you can unpickle it and load it back in. This works great unless you have a custom class. Then sometimes get into trouble, and there's like rules. You can't pickle functions. If you want to do that, use Cloud Pickle. So that's a cool thing. All right, let's go over here. We got our seed random number generator with random streams. Recall, that's the RNG we use, this MRG thing with the super, super long period. Totally unnecessary, but that's okay. Now we're going to start building up our necessary group of sort of like helper functions that'll let us build this convolutional neural net. So there's just a few things we need here. So we need floats. And we need to turn things into floats, I should say. And I don't want to have to do this Numpy as array thing every time. So we're just going to say float. And it's an array not of just traditional floats. It's an array of, note this dtype Theano.config.floatx. X dtype, so that's a data type. Theano.config.floatx. Double check me. Perfect. I like that. It's lined up perfectly. So good. So that's just a convenience. What do we got next? We got to initialize our weights. Init weights. Shape. So we're going to pass in some shape like 2x2 or 3x3 or 625 by 1, whatever. And we're returning Theano dot, I can never remember the shared, yes. Dot shared. Shared means from sort of when we actually evaluate the model from one step to the next, keep this value around. So sort of like a static function in C. That should be that. And what are we going to do? We're going to call floatx on whatever the heck it is that we're putting in. And that's going to be not shape, but it's going to be, yeah, numpy.random. So we're going to fill up some random numbers. Do I know Python well? I do feel very comfortable with Python. I'm not as comfortable with Theano. That's why I keep flipping back and forth. I think I've been using Python for, I guess, going on 7 years. I started picking it up in grad school. I should have started sooner. I think if you have to pick a programming language to learn, I would just learn Python. It's very popular. It's pretty easy to do. It lets you focus on sort of the task at hand rather than the computer science issue that you're going to have to deal with. If you want absolute speed, you're going to have to learn like C or something like that. But if you don't need absolute speed, what am I doing here? Hang on. There we go. And Python, because there's so many libraries for everything, half the problem is going to be you're always learning a new library to do something. If you try to implement it yourself, like often you can do that, and that's fine. But the catch is it's going to be slow if you implement it purely in Python. I think a couple weeks ago I had implemented like a multi-layer perceptron maybe. No, I didn't do that purely in Python. That was with Theano again. Whatever. I've seen guides that walk you through that, and often that's a good way to do something so you understand what the hell you're doing. But that's not a good implementation. Maybe you should do that and say interesting, and then set it aside. Okay, so we did our initialize weights. We initialize it to a random Numpy random array of small numbers. Random.randn returns numbers between 0 and 1. We're going to make these between 0 and 0.01. And this star business, you don't see that often in Python. That sort of unravels a shape. So if I just real quick pop over to my actual Python session, define f of a comma b. Let's just return a times b. So I could say f of 2 comma 3, and I get 6. That's fine. Now I say c equals 2 comma 3. So that's sort of like my arguments. I can't just call f of c because it's expecting 2 arguments. But if I say f of star of c, it sort of unwraps that if you have a list of things and it makes each one of the arguments. So that's what we're doing here. Because numpy.random.randn can sort of take a variable number of arguments. So that's nice. Anyway, rectify. This is the activation function that we're going to be using. So whenever anything goes through one of our neurons in our neural net, it's going to have some value going in, and then that value is going to be sent through the rectified linear. All rectified linear does is it's almost the identity. Whatever number you put in, you get out, unless that number is negative. If it's negative, then you just get back 0. Let me do a super simple example. Numpy.max x comma 0. And let's do plot of rel u of x. That's t. So I'm just doing a quick example. For t in range of, I don't know, negative 10 to 10, whatever. Is that gonna work? Bing, that didn't work at all. Well, that's hilarious. All right, well that worked, not at all. Numpy.max, oh, hang on. Let's put these all on the list here. There you go. So as you can see, it's like the typical linear y equals x shape over here when we're at, the hell's going on? Yeah. No, wait. If x is 10, this ought to be 0. If x is 1, buddy, this should be 1. Alright, that's the right shape for LU, but somehow it's gotten shifted. That's in the wrong place. That is quite the mystery. Quite the mystery. LU of 5? 5, yeah. Do I not know how to use list comprehensions like I thought I did? Oh, no, I see. I'm not actually plotting against the correct. I was just plotting versus index, so it was going this 0, this 1. And my index is off by 10. I'm glad, thanks Roma. I'm glad you enjoyed explaining the star. That's one of the weirder things in Python, so. Anyway, that's the right shape. It was shifted by 10 because I wasn't actually plotting real x values, which I can do, and we'll get to that later. Anyway, that's just the activation function. So you need that to sort of make your neurons actually nonlinear. Note this is almost linear. If you're always positive, it's basically always going to be linear. But sending things that are negative to 0 it's been shown to work well for image classification problems. All right, softmax. This is what I also call logistic regression or multinomial logit. This is not really that complicated of a function. It looks pretty bad. Basically, if you've got these 10 digits, we're gonna have a little score for each one of our digits based on whatever features we're throwing at it. And so you're gonna have a score for your first digit that is like a whole bunch of weights times a whole bunch of features, and those features are gonna come from, or those weights, yeah, those features are gonna come from our neural network. And so that value, those weights times those features, that's what our x is here. You've got a score for each digit. This softmax just tells you how to combine those to get a probability that it's a certain digit. Basically, you take the score for your given digit and you just do the sum. But here you put in this score and it's e to that score. So it's natural log base e, numpy.e, yeah, that number, divided by the sum of a whole bunch of e to all the scores. So it's just like a fraction. It takes whatever number you computed and puts it in this range of 0 to 1. And this has been shown to be desirable for a lot of classification problems. This has been used for a long time, long before, I don't know about long before, but it was popular long before neural networks were popular. I'll say that. I used it a lot in grad school. It was a great place. But in the neural networking world, they like to call it softmax. So I'm not going to argue with that. Dropout. What does dropout do? Implement random dropout of some neurons during training. So one of the problems with overtraining in neural nets, you've got so many features. It's so easy to just sort of memorize the data with all these features, and then you haven't really learned anything, you're going to look at some testing or validation data set, and you're going to be totally wrong, because all you did was memorize features that don't matter, kind of thing. Dropout says when you're training, there's a certain probability that you're just going to remove a particular neuron and not use it this time. So it's just going to pass on a value of 0, say. If p is greater than 0, yeah, this is where we're using our random number generator. That's where we're going to determine what the probability is that we actually keep this x. And then you just return that, whatever that value is. So you don't have to do this, but this often gives you a better network. It helps avoid that overtraining. Nope, we're going to use the dropout when we're training. When we're actually using our network to predict, we leave all the neurons activated, because we just randomly choose neurons that drop out in any given iteration. All right, RMS prop. This is a complicated one that I also don't want to retype the whole thing. So I had to look this up a little bit. In fact, let me look it up again just so we can see. So this is what's doing the gradient descent, though. That's what the important thing is. It's doing gradient descent with regularization. And that just means that we're penalizing our model for having very large and lots of parameters. Scholarly articles. I didn't really want scholarly articles. I just wanted articles in general. Oh, clearly I must have looked at this page. Right. In fact, RMS prop for a long time, I don't know if it's still true, was only ever referenced on someone's slide in an important talk. Where is it? RMS prop. There we go. Per parameter adaptive learning rates. Very effective, but currently unpublished. Yes, it's just on this one particular slide. I don't want to go into this too much because it's probably not, it's going to be too many details for just this talk. But this is our gradient descent, essentially. So when you get to the end of your neural net, you've done the forward activation, and you get the score at the end. You compare that to what the actual digit is, and use this information to backpropagate, is the proper term, the errors to fix up all your weights a little bit. And that's about as much as I want to go into that right here. The key gradient descent is what's your old p, and it's your whatever your p is minus the learning rate times g, the gradient. That's sort of the short of it. And you fiddle around with the gradient in special ways using this RMS prop algorithm. But the key is that it gives us updates, and that's what we'll pass to Theano to say, hey, fix these things. All right, what are we doing next? We're doing the actual model next. So I just want to copy this line. So that's now we're going to build the actual model. And our model is going to have, apparently we've decided, I think 3 hidden layers, maybe 4? I think 4 hidden layers. Yeah, 4 layer. It might be a 4-layer model, 3 of them might be hidden. Can I send you that link to the RMS prop? I probably can. This is the problem of me watching the stream on one computer and using it on another computer. Let me check that real quick. .io/neural networks. Now you can like hear how slow I'm typing. Star Ada. CS221 to get him to IO. Yeah, no problem. Glad to help you guys out. Where were we? Yes. So here we've got 4 layers. 3 of them are going to be convolutional layers. The last one is just going to be a full standard fully connected layer. And then that's going to feed in to our softmax, to our classification. And we also need, what's the probability that we drop in the convolutional layers, and what's the probability that we drop in the fully connected hidden layer. All right, so how does this business start? So our convolutional layers, we're saying it's a convolutional layer. It's really got this 2 components. it's got this convolution, ReLU, as I called it. Rectify. And what are we rectifying? We are rectifying, we got to use conv2d. That's where this business comes in. Conv2d, remember we pulled that out at the beginning? And what are we doing? We've got our x and we've got our w. How does conv2d work? That's what we have to remember. Oh my, that's a lot going on. Build a symbolic graph for convolving a stack of input images. So that's our inputs. And our filters is what the next thing is, with a set of filters. So our filters is, I believe, going to be the little boxes. Let me see if I can get that right. W. Oh, W is, sorry, that's not our little boxes. That's the features we're pulling off using those boxes. So our input image, X, W, the first layer weights. I could have called it W1. In fact, let me call it W1 just for posterity. And then what is the shape? And this is where it gets a little goofy. It's a 4-dimensional tensor. It's, oh no, I guess it gets inferred. Never mind. We'll get to that in a second. And we have this border mode business. And this took a little time for me to sort out what exactly it did. So if you've got some silly 3x3 box that you're dragging along your image is 28 by 28, remember. There's the question of, what do you do when you get to the end of a row? You're in the last row or the last column or whatever, and you fit your 3x3 box in. Do you step it over one more time, and you've really only got like a 2x3 section now, and those other 3 slots are sort of off the image? So when you say border mode full, I believe what that's doing is you still, you know what, let me just look right here. 0 pads image, yes. Yeah, so that says do it anyway, even if you don't have a full, even if there's no image in part of the slots, just put zeros there. So that's what full is going to do. Otherwise, you can say do valid. So only apply your little 3x3 box on places where it fully fits, where it fits within the image entirely. Got to make sure. And they give you little formulas for here for figuring out what your output dimension is going to be. So if our image shape is 28 by 28, your anchor for that 3x3 slinger is in the center, top left. We're going to be dragging it everywhere. So our first one is actually going to be, let me open up GIMP. That'll be the tragically easiest way to explain this. Our very first one is going to have just 1 pixel in it. It's going to be a little silly. All right, here we go. So let's say the black is our actual image. We got this. Beautiful pictures. Then we got some red here. Ding. You are actually going to start, oh no. You are going to start, let me make this smaller. Over here. Because we're doing border mode full, remember? And so really, you're only looking at this single pixel at first. So yeah, you started in the very top left. And then maybe on your next, depending on what your stride is, you'll move it over. And so you'll move it over to the right 1, say. So you're going to overlap a whole bunch, and that's okay. Nothing wrong with that. And then you'll be here. And so now you're really only looking at 2 boxes. And this is because we're doing border mode full. So all these other boxes, these empty boxes, those are just gonna be filled with zeros. So it's as though the image were larger than it were and had some extra zeros in there. For the other layers, everything but the first, I think you only do full. And so just to give a visual, doing full would mean starting here. You start at this section, the first completely valid, and then you would use all 9 of these. Okay, so I hope that worked out pretty well. My beautiful mouse art. Okay, let's keep rolling. So you have to do this convolution. That's the first thing you do. You rectify on that convolution. That's your activation. And then you have to do the max pooling. And I want to see what variable I call it. L1 is just all. Okay. So L1, and that's where we conveniently have our max pool 2D, I believe. Yeah. And what are we doing max pool 2D on? Well, just whatever the activations were that we got. And we need to say how big is our pooling. It's very typical to do this 2 by 2. So to go back to GIMP, you're doing the max pooling on these 3 by 3 blocks that you've got. That you've got the 3 by 3 block. You pull out a whole bunch of features from that. Let's say you're only pulling out one feature though, and let's just do the stupid thing. Let's suppose that feature was adding up all these numbers. That means you've got a number in this block, you've got a number in this blue block, you've got a number in this red block, etc., etc., etc. For adjacent blocks, we're going to take whatever that feature is and take the maximum, only the maximum. We'll throw out the other 3. So I've got this sort of cyan color here. That's a block. And let me get some yellow real quick. You got one down here somewhere. Note that these overlap a whole bunch. Just the way it is. They don't have to. That just happens to be the way these work. And your last one would, I guess, be right here. There we go. So each one of these different colors, apologies to anyone who's colorblind or to anyone who's impossible to follow image I have going on here. Each one of these colors, the green, the cyan, the yellow, the magenta, is going to give you one number. So you're going to have 4 numbers there. That's going to give you sort of like another little, imagine this grid off somewhere else. Max pooling says look at those 4, and just take whichever one gives you the highest, and throw away the other 3. An important catch, you're not going to do overlapping. So you're going to look at those 4, and then you're going to go over 2 more. And then you're going to look at those 4. That's all the max pooling does. And this max pool 2D does that for us. So that's great. And I know we're spending like a lot of time getting this together, but then we're going to be, once we get it correct, it's going to be much quicker. And then finally, after you do the max pooling, then we sort of randomly throw out some of the neurons. That's what the dropout is for, and our probability of dropping a convolutional layer. So that's the first layer. First layer. Then we can do the second layer. Because the second layer, you're going to notice, is very, very similar. In this case, for this particular model, we're taking out the border full. So that means we are only sticking our little, I like calling it the slider. We're only sliding where we have all valid parts of the image. So valid is the default behavior. And you can see that over here. Border mode equals valid in the conv2D operator. I want to double check that I did that right. Yes. Cool. Note, we haven't actually specified here how big a window that we're sliding around. We're going to specify that when we specify the W1 value. It's going to infer that from the size of that tensor. But I think L2, yeah. So that's L2. That's make sure you update all the variables. So L1 is going to go into here, and this is using weights 2, right? Yeah, down here. and then you take the L2A and you drop out from L2, things that you can get burned on if you're not careful. Let's work on a third layer then. Third layer is, I believe, another convolutional layer. Yeah. Typical thing. Boom. Vim is so good. I love this. Don't try to do conv 3D. You gotta be careful. 3. And if you were good, you could set up a little function to do this for you. I kind of like to see that I've specified the layers in this way, so I'm not doing that here. All right, now we have our fourth fully connected layer. And so what are we doing here? We can say L4 equals, is it softmax, I believe now? No, rectify. Sorry. We're rectifying, but we're not doing conv 2D. We're just saying, hey, rectify L3, and we've got W4 our weights, by the way. That's not going to work. Yes, we have to dot them. It's the output of layer 3 times the weight for whatever that is. So close. So tensor dot dot. And so that's the sort of the standard thing to do there. So that gives you the activation. Do we drop it? We do drop on this layer. We don't do max pooling because it's no longer a convolutional thing, and there isn't this sense of this neuron is next to this neuron anymore. Isn't coming from, oh, did I have a typo in my? I think we're okay. This comes from L2 in the third layer. So it needs to come from here. And then max pool to, it's LA. L2A, L3A. I think we're okay. Inevitably, we will find out what typos I made, and then I will go back and see how you were correct. Right now, I want to try to finish this. I think we're all right. Anyway. L4 equals, note that we're overwriting this variable. That's okay. You can do that. No big deal. We're going to drop out on L4, P drop hidden. 8. I appreciate people double checking my work. That is helpful. I will inevitably make horrible typos and miss really obvious things. I know when I've watched people streamed, I have occasionally yelled at the screen thinking, "You idiot! Can't you see the super obvious thing that's there in front of you?" And the answer is no, you can't see it. Because you're trying to talk and do everything at the same time. Okay, finally, so this is our fully connected layer. Then we just need our actual classify the output. So now it's like the output of this fourth layer is just a whole new set of features. And from that, you can do whatever. You can do your regular standard classification stuff. So we're calling that softmax function. And we're doing our standard layer t dot dot, whatever the output of our previous layer is. That's L4. Also looks like 14, but it's not. And we use WO. I don't remember why it was called O. All right. And the question is, what the heck are we returning from the model? And the answer is a lot of things, because we want to see some internal output. We want to see sort of the activation of every layer. And remember that these are just the Theano, like the graph computation. Oh, important thing, PYX. This is probability of Y given X, our input image. And so it's going to provide us with a probability for every digit. And those really ought to add up to 1. If they don't, we did something very, very wrong. So that's the core model right there. That only took us 45 minutes. Look at that. That's why I showed all the cool pictures first. All right, this stuff I'm going to try to blitz through pretty quick. Let's grab ourselves some data here. This is our training X set, the images. Our testing X set, also images. Our training Y set, just a couple of labels. And we use the one hot true That means every label is going to be 10 numbers. 9 of them are zeros. The one that's a 1 tells you which digit it is, its position. So that's an inefficient way of storing that, but that's super handy for doing dot products and stuff. First thing we need to do is take our image and reshape it. And we're going to turn it into this 4-dimensional tensor object. Let's see if I can spell. So we've got 60,000 images. We've got one channel because it's just grayscale. And it's a 28 by 28. Yeah, I know there's a fair bit of lag in the stream. I don't have a good way of improving that. I'm not at the point where I want to pay for better internet because internet is way too expensive. All right, so we've reshaped. I think, well, let's reshape that too. This is just to take a look. Let's take a look at one of our images. It's a super good thing to do. Always look at your data. Doesn't matter what it is. Open up the text file, see what it looks like. You might see something really obvious. So we're going to grab the first image, or the second image actually, because Python is 0 index, and then look at the first channel. It's just grayscale. There's only one channel. If there were colors, you could specify which one. And we're going to plot that. And this one is probably a 0. Just a guess. Just a guess. Let's look at one more, just to try it. Let's look at the first one. That looks like it's probably a 2. Probably a 2. So maybe I was looking at the essence of 2s earlier. We'll find out. What do we got going on? Then we got to specify. These are sort of our Theano inputs and outputs. This is our input, X, recall. This is a float, the F, tensor 4. So this gives us a 4-dimensional tensor. Tensor type float 32, so it's 32-bit floats. The .f matrix says it's a 2-dimensional tensor, and it's a matrix, so it probably has lots of other nice things that come with. All right, let's grab all our weights here, and then I'll explain them as we're going along. You know what? Let me grab one, and then I'll do it. So this init weights, that's a function we wrote earlier that gives us random weights to start. Note that we're passing this as a tuple because it just takes that one shape. So don't pass in 32, 1, 4, 4. You have to put an extra set of parens around that. This 32 says, how many features are we pulling out of this first sliding window? 32 just happened to be what the model I had was. You could pull out more, you could pull out fewer. Pulling out more and more is sort of saying, I want more and more information from this, knowing that some of them are going to be bad and maybe you risk overfitting. One says, how many channels do we have? We have one channel. In this 4, 4, this is the size of our window. I believe this is the X size and this is the Y size. I almost always see squares. So these numbers are usually the same. The initial model was 3 by 3. I decided to up it to 3 by 4 just for giggles. We're going to call that W1. W2 is going to be very similar. I believe it's 64 and then 128 is how this is going to work. Note that we're pulling out more features. The next layer is reading from the output of the max pool of the previous layer. So we're no longer looking at pixels. We're looking at activated regions of these 3 by 3 blocks. But we happen to be doing another 3 by 4 layer. I lied. Okay, I didn't lie. So you've got 64 output features, and you've got 32 input features because you've pulled off that many features from the previous layer. And this sort of continues here. Do I have W4? Is that a thing I have? It is, okay. W4, this one is a little different. So these first 3 layers, those are the convolutional layers. Those are like you would expect. We have chosen to make them each 4 by 4, but they do not have to all be the same shape. W4, however, happens to have 625, I think, features. No, that's got to be wrong. Oh no, it's got 625 outputs. It happens to have 512 inputs. And that's sort of how many That's at the end of all our convolving and our max pooling. That's what we end up with. How many sort of, I'm going to say, faux pixels. And I'm going to real quick try to explain how you arrive at that number. Okay, we start with a 28 by 28 image. Let's just work with one dimension so we don't go bonkers. You've got 28. You've got this 4x4 sliding window. If you recall from from conv2d, what you end up with when you're doing when you're doing the padding, you get image shape 28 plus filter shape 4 minus 1 gives you 31. 28 plus 4 minus 1, that gives you that 31. That's after the first layer. You've got sort of a 31 by 31 block of things. From then on, you're no longer doing the padding, so you need to subtract however big your window is, minus 4 plus 1. Minus 4 plus 1. I lied a little bit. You've got this. You're doing the max pooling. You divide by 2. Why are you dividing by 2? Because you're doing this 2 by 2, and you're not taking any padding. And I think even when you do this max pool, you round up. That is, if you have at the very end of your line, you just got 1, 2, and next to it, it would be off the image. You just set those to 0. So you're sort of padded. Yeah, I believe is the default behavior for the max pooling. Let's do numpy.seal. Let's just do that for the first layer. Boom, and you end up with, you've got a 16 by 16 thing going into the next layer. And then you repeat the process. Now you would have numpy.seal of 16 minus 4, because it's no longer padded, plus 1, divided by 2, gives you this 7. You play the same game. So you have sort of a 7 by 7 block of things you're taking features on. Then after the third layer, it outputs sort of like a 2 by 2 block after the max pooling. And that is where this 2 by 2 comes here. You've got 128 features you pulled off of it, times 2 times 2. This took me a little bit of time to get my head around the first time I did it. Drawing a picture is often very helpful. And it just so happens that we're going to have 625 outputs. I don't know if that's because 25 times 25 is 625. We'll see. All right, what are we doing next? Let's blitz through this. Oh, we need our final layer of outputs, of course. So the W0, that just says, hey, take the output of that final fully connected layer, the 625, put them into our digits, put that into our softmax. And so from these shapes, Theano knows what to do with this model. You could fiddle around with these shapes and use the same model function. That's a nice thing Theano can do for you. All right, we are almost there. We are almost there. We've got 5 minutes. There's always never enough time left. I'm going to just copy things. Boom. This first one, note that we're calling model over here with our symbolic X and W's and whatnot. This one, I believe, just gets used for training. Is that right? Am I crazy? Yeah, I think that just gets used for training. This one actually gets used, yes, it gets used for training because note that these are the drop probabilities. In our convolutional layers, 20% chance of drop. In our fully connected layer, 50% chance of drop. So half the time, we're going to lose a neuron in that layer. That's fine. And then this line will be used for prediction, not question mark. I'm Ron Burgundy? No need for that. But you've got the same inputs, you know. And then you make some predictions with that. You use whatever the outputs are, this PYX, the probability of Y given X. You take it along axis 1. That just tells Numpy you've got some multi-dimensional thing, which way you're taking the maxes. Am I limited by a time limit? I try to only stream for an hour because my voice will start to get tired. And I was using my voice too much yesterday to begin with, doing some silly voices. I'll go over maybe 10 to 15 minutes if we have to. I don't think people want to watch videos that are that long anyway. What do we got going on next? Important. Cost function. So we're doing this fancy categorical cross-entropy business. You don't have to think about that too hard. You just have to know this is what we're using to tell gradient descent how to. This is what we're optimizing. We're going to minimize this cost function. And basically it's, well, what was our training predicted y value versus what was the actual digit label there. That's all. This is a podcast. We can watch this all day. I've definitely done that with some podcasts. I like to do it when I'm driving. I do not recommend watching this video while driving. Do not do that. Unless you have a self-driving car, even then you probably shouldn't. Self-driving car, I'm looking forward to that. And by looking forward to, I should be working on that, but I haven't gotten around to it. Params, this is just how we're going to collect all our weights from Theano. And that's how we're going to tell it what to update. So it's convenient to collect those all together in a list. And this is where we call, hey, RMS prop. That implements our fancy gradient descent. I happen to have a really small learning rate here. Don't know why that is. And this, we're going to have this variable updates, and we're going to end up passing that to our Theano function. All right, a couple key functions here, and then we will be ready to do it. So training. This is the function that's actually going to train our weights. So what do you input? You input your images and your labels, whatever digits they are. What's the output? We're choosing to output the cost here. Really, we don't actually care what the output is. We just want to actually do the updates. That's this section. We want to update the weights. Allow input downcast equals true. I don't 100% know for sure what that is. I think that's if you pass it like a float 64 or a float 32, it'll automatically cast it to the other. So if you take 64 bits for a float, it'll say, throw away some of the bits. We'll just use 32 bits. Let's take a look. We always have time to look at man pages, right? Let's search for downcast. True means that a value is passed as inputs when calling the function can be silently downcasted to fit the D type of the corresponding variable, which may lose precision. Right. So if we pass in a 64-bit float, Theano is allowed to say, we're only going to do a 32-bit because that's much faster to compute on in our GPU. So that's a common thing you'll see. Again, this is the function to train. We input the X's and the Y's because you have to know what the labels are to train in this case. We're doing supervised learning. Then down here, we've got our function to actually compute the output. So we still put in our X, but what do we want to output? We want the actual probabilities, YX, which is, recall this line up here, which you might recall uses the regular model with no dropping. All neurons are included. Okay, and then I have this kooky scheme here on how I'm actually doing the training. And that's just to see some things that happen along the way. But that's, you can just do this however you want to do. In fact, I'm going to say I equals 0. So typically people like to train these things in what are called mini batches. So you can like read in all the data at once, all 60,000 images, compute all the scores, and then update the weights. But typically you can get your own. You could just do a couple at a time and update the weights, and then do another couple, and then do another couple, and then do another couple. So that's what a mini batch is. In this case, I'm computing how many mini batches do I have, and I'm saying I want to go through the data 100 times. We're not actually going to go through the data 100 times, but that's what we're saying. Start equals 0, end is going to equal 128, I think, right? Let's see what happens there. So we're doing mini batches of 128 images at a time. It claims there are 469 of them because 469 times 128 is just over 60,000. Whew. All right, so first you train the model on these few. So we're calling train, and you say, hey, put in our actual images as the X value from start until end, and that's just which mini batch we're on. And you put in the same labels, the corresponding labels, I should say. So what is our actual cost? You get some float. This is not going to be, in general, human interpretable, but that's okay. This business here is just for printing that the model is actually doing something. In this case, I've already trained the model. I was running this while I was talking initially. So let's go back and take a look at what we did again. This w.getValue business, that's how you actually extract the literal value of a certain tensor. So normally w is whatever. If you say w dot, and it comes up with all these things, get value. Then you get the actual values, which is always nice. That's what I like to see. This business is just to make a subfigure. So I've got this SX, XY. This is how many rows do I want? How many columns do I want? I actually want to change this from 4 to 8. That would be great. You know what? No. Keep that as is. I'll leave it fine. And you say plot.subplots. So plot was our matplotlib, remember? And we have sx comma sy. That's how many. That's sort of the grid of our plots. This sharing business, we're not actually really going to use the axes on these plots, but this way we sort of minimize the number of axes that we need to get at least some sense. So the share x col says, well, you'll see. Every plot in the same column has the same x value, and something didn't work right. Why did that happen? Not enough values to unpack. Expected 2 got 0. Oh, because it didn't actually do WW. Maybe. Let's see what happens. There we go, yeah. And so these are actual weights. So you've got 4x4 pixels. You can start to see what the values are. And I believe, let's take an actual look. So WW is where I stored the real values. WW of 0. So this is a 4x4 blob. So the more negative it is, the darker it is in this case. So the very, very light squares are the ones that give you high activations. Recall that the negative ones, we've got that rectify linear. So if things are very negative, they're going to end up just going to 0. That's just the kind of the way that goes. And actually, WW 0, 0. There's like another layer of arrays here. This is one of those things that you got to deal with to make all the math work out. And then you can look at the next layer too. I don't have a good way to take a look at the next layer's activations relative to the first layer. So each one of these guys is on one of the previous layer's activations. So I'd like to be able to like look at this and say, well, take whatever the first value of the first layer was and multiply it by whatever number's here, and so I could see a bigger image, and so you could start to see larger scale features. People have done this. I just haven't sorted out exactly how that's done. And there's much cleaner ways to clean up these axes, but I don't really care about that. That's a small distraction, and I kind of like having a border between all of them, so I don't start to see a picture in the picture. Try to magic eye this. I'm gonna do that right now. Yeah, all right, I don't see anything. One thing we could do, if you don't like grays, you don't have to. So I'm using the color map gray there, gray reversed. You can do colors. Bing. And this is the same plot as before, but the blue is very low and the red is very high. Same thing. I just happen to like the grays more for this. The color is actually a little distracting. Often I will do the color though, and I prefer that. All right. One more thing. I've already loaded this dream model stuff. So this is starting with random input, a init rand image. This is just like our sort of init variable, but we're just making it random. And I'm using rand, not rand n, because numpy.random.rand, this gives me values between 0 and 1. Rand n gives me values that are normally distributed. I got that mixed up earlier. I apologize. What kind of sample does your program go through? Just images? Yes, I am just working with the MNIST dataset. If you go to that web page I linked, I believe, or no, not the one I linked, the one on GitHub. I'll leave a link in the information or the comments. That shows you the actual data. And in fact, we plot. There we go. This is one of the images. So all the images look something like this. Let's look at a random one. And by random, I mean 7. So that's clearly a 3. Let's look at the last one, just to show you what these look like. I'm pretty sure that's an ampersand. Maybe a musical clef. And possibly after that an 8, I would guess. Or it's like, it's a Pokemon, it may be an oddly shaped Pokeball. Anyway, so note that our model is pretty much exactly the same. The catch, the only different thing here is X is the same. This one might actually be exactly the same. I flattened. Did I miss the flatten? Oh my gosh. I forgot to flatten. Whoops. So important note. You've got this weird like matrix of neurons at this layer. You need to flatten that out. But that's outdim equals 2. I don't know why I'm taking time to fix that up. But yes, because the next full layer is expecting it to be full. Okay, so you've got this dream model. This is basically the same. I think it's exactly the same. I might have just redone it. And I'm going to create, say, hey, give me a dream thing. The catch is I'm putting img, this random image in. And by random, I mean it's a Theano shared variable, just like the weights. That's the key. It's just like the weights. Because we're going to be climbing on that. I'm going to say, given a particular label and a random starting image, give me some new output image. Tell me, I want you to tune the parameters, the image itself, to give me something that looks like that. So this is sort of like, what does the model think this particular thing looks like? You do this by changing the input image and by doing this ascension, gradient ascent instead of descent. Because now you've got some cost where you're trying to maximize something. I might have this mixed up. I'm not going to lie. That could be totally wrong. Can you make lewd jokes? I can't stop you. The worst thing I could do is ban you. I certainly curse a fair amount in here. I would say don't make unnecessarily lewd jokes. Yes, so you got that. Got this. Otherwise, pretty much the same cost. What do we think our y is versus what is a y actually? But our parameter this time is just the image. I'm not changing the weights. I just want to change the input image. And you do the updates. We compile our Theano function. Our inputs this time are just the label. So that's the opposite thing. What are the outputs? The output is just our new updated image. And so that's what we're going to do. And I guess I do this for 16 times on the first image. If you recall, this image looks like, I think, a 2. Yeah, this looks pretty solidly like a 2. Not 100%. Pretty solidly, though, I'd say. And let's compute that. Int object has no shape, of course. My own code denies me. I tell you. Nope. All right, it doesn't work anymore. All right, hang on. Well, we had it work. We had it work before. That is true. Let me just run all this garbage again. Let's just do that, shall we? That should be fine. And then I will wrap up here real quick. There we go. So this is the essence of a 2, I guess. Which, this looks kind of backwards, you might notice. Well, things happen. What if we try to do the essence of a different number? We just change this. For example, whatever the first one is. Let's see how much that works. I meant to rerun that whole section. Oh, yes, we do have to rerun that whole section because our image right now has... we put in the essence of 2 and we're trying to change that to something else. Although that can lead to an interesting situation. So our network is sort of said to be dreaming, given random input and iterating on that until it gets to what it believes is a 0 or whatever. So to me that looks like essence of 3, but I'm pretty sure this was supposed to be a 0. Oh well, that's what happens sometimes. All right, I think I'm gonna call it there. We've got to play with some things. We got to look at some cool pictures generated by our neural network. If you have more questions, send them in the comments or drop me a line. I'm on Twitter, or just send me an email, whatever you like to do. And you guys have a good night. Keep on learning.